Hey everyone, I know you're very hungry and it's almost lunchtime. But before we break out for lunch, I just want to invite you for a quick journey exploring zero knowledge proofs and specifically how you can use them in Ink smart contract language. So, a little intro about me. My name is German. I'm a Rust core engineer at Parity. I work in the Ink team. I'm also one of the alumni of Polkadot Blockchain Academy. Aline and I are going to talk a little bit more about it tomorrow, so make sure you tune in. And essentially, again, we're basically going to explore zero knowledge proofs and how we can use them in Ink. And before we start, I want to give a little footprint. So if you're not a mathematician or a cryptographer or a computer scientist, don't worry, me neither. So you don't need to know all this maths and cryptographic stuff to understand the content of this talk. I'll try to keep it as high level as possible. And the whole purpose of this talk is to basically, show my personal experimentation around the topic. And to give you a background story behind this talk, I basically got interested in zero knowledge proofs roughly a month ago. And because I work on Ink, I decided to basically go on this journey and basically just play around the language, play around different technologies and see how we can basically use them inside the Ink. Specifically, how can we write a verified contract using Ink smart contract. So now let's quickly go through the agenda. So if you haven't listened to Damon's talk about Ink and how awesome it is, I'll basically give a quick introduction about Ink, what the public contracts is, what substrate is. If you have, then we basically go through this section very quickly. Then we'll basically move on to overview of modern ZK solutions. I'll just basically present you with popular libraries and languages of zero knowledge proven systems and different high-level languages and how you can use them. Then we'll move on to the actual part, specifically what you can do with Ink today and how exactly you can, write a verifier or a proof inside the Ink smart contract. And then if I have time, hopefully, I'll show a quick demo of how it can be done. Then we're going to discuss about the current limitations of the ecosystem of Ink and current limitation of zero knowledge proven system and languages. And then we're going to finish off with the road ahead, the future ahead, and how we can essentially develop further. Again, the whole purpose of this talk is to kind of show you the current developments and essentially share my excitement about the technology and essentially provoke the discussion. I'm going to leave some socials on the last slide and encourage you all to essentially discuss this topic further with each other or with me. So now let's begin. Just before I actually dive into Ink and Substrate, just want to ask you a question. Raise your hand if you have used Substrate before, you've heard of Substrate, or you know how it works. Okay, so I'll just confidently say it's half of the audience. So Substrate is open source blockchain development framework developed by Parity, and it allows you to develop your own runtime and nodes in a modular way. And the modules in Substrate are called palettes. And with palettes, you can essentially compose your runtime and provide the domain-specific functionality. And essentially, most of the parachains, if not all of them in Polkadot ecosystem, are developed with Substrate. And Parity provides a set of maintained and well-developed modules. And one of them that we relatively recently developed is Public Contract. And Public Contract is a WASM execution environment that allows you to compile any code written in a high-level language down to WASM binary and execute it on chain. And then we have Ink. So Ink is essentially embedded domain-specific language, but this is kind of fancy definition. To put in simple terms, it's basically Rust with macros. If you're not familiar with Rust and macros, it's basically a library that allows you to take a bunch of Rust code and turn it into intermediate representation and then compile it to WASM binary, which can be then interpreted on chain. And the reason why we chose Rust is for many reasons. Is first-class WebAssembly support, small binaries, type safety, and fast execution times, which is essentially all the necessary requirements for the smart contract language. And then we also have this user story that if you're a Substrate developer, then there's a very easy and smooth developer experience, learning Ink from Substrate because it's the same language. You can use almost the same libraries, but I'm going to touch on this later. And then essentially you can prototype your runtime with Ink, and then if the POC or proof of concept works, you can essentially implement it in Substrate. So just to give you a little illustration of what the Ink program looks like, if you have a look at the slide, you can see that all the white text is basically normal Rust syntax. And then we put a bunch of macros, attributes on top. These are the Ink macros that essentially turn this Rust code into intermediate representation. So it's basically, it does some magic behind and allows you to compile your normal Rust program into a smart contract, essentially. So having this out of the way, again, I'm just going to quickly go through the points why Rust. Again, efficient, first-class wasm support, and we also benefit from the crate system, from the library system, the whole Rust ecosystem. We don't need to maintain the compiler, the tooling around it, because it's all essentially developed by the community of Rust. Okay. So moving on, before we talk about zero-knowledge proof, zero-knowledge proof systems, I'll just quickly give a definition of what the zero-knowledge proof is. So again, this is a very boring definition. Essentially, zero-knowledge proof is some sort of process that essentially, in which process one party, in this case, a prover, tries to persuade the other party, verify that some statement of some sort is valid. And the part of zero knowledge is essentially we are doing that without revealing the input. And the whole idea, like in the context of smart contracts and computation, so what we're trying to do is we're trying to prove that some sort of abstract computation and the result of this computation is indeed valid without actually going through the computation and executing it. So essentially, verifying the result of computation is sublinear to actually, running the computation on its own. And there are different sorts of flavors of zero-knowledge solutions and how you can use them. So one of them, there's some libraries, there's some languages, there's some high-level languages, low-level languages, domain-specific languages, and embedded domain-specific languages like Leo, Carrera, and they target different architectures and different ecosystems. But you can essentially categorize them into independent families. It's either Stark or Snark, and it's either you work in high-level language, or you craft relations and circles by hand. And sometimes you just need to make the certain trade-offs, between different sort of family you wanna go for. So if you work in high-level language, you always pay with the proof size, and there's certain overhead in computation. Crafted relations requires a heavy knowledge of cryptography and math. Stark and Snark is essentially a different proven systems. And with Stark and Snark, you essentially need to have a trusted setup, which may not be favorable in your use case. And with Stark, the setup is transparent, but you pay with the large proof size. There are certain developments where you can reduce this proof size, but I'm not going to go into detail. And we have, I'm sure we have some people in the audience who are more knowledgeable on this topic and can tell you more about how this can be done. So now moving on. So Ink and zero-knowledge proofs. And the answer to your question, is it possible to actually write zero-knowledge proofs or use zero-knowledge proofs inside Ink? And the answer is yes, you can. Technically, you can. So you can use any of the libraries that are out there on crates.io, and you can use them right now in your Ink smart contract and Ink project. Again, I'm going to show you in a demo in a minute how you can do that with certain constraints. So the library, it should be no STD, so that means that it should compile without the standard library. Then due to gas instrumentation, there are certain limitations on also the arithmetic operations that are permitted inside the library or your code. So specifically, you cannot use floats. And the third point is you cannot, so the proof size should be relatively small. And why? The reason for that, again, I'm going to touch on that slightly later. But then we can also slightly overcome these limitations with the concept of chain extensions. So chain extensions is, again, one of those killer features of Ink that essentially, in the short summary, you can expose a certain domain-specific functionality from your runtime, from your substrate runtime to Ink, and allow smart contract developers to essentially make a calls to the runtime and execute the code not inside the WASM interpreter execution environment for smart contracts, but on the level of the substrate runtime. And for the demo, I'm gonna showcase this chain extension that can be used inside Ink, and specifically we're gonna showcase how you can write chain extension with RISC-0, and how you can submit the result of verification of proof back to the contract and essentially report back to the user. So now moving on to showcase. So this is the kind of rough overview how the demo works. So we have our Ink smart contract, which then sends the proof to through the chain extension. Chain extension is essentially it becomes a part of runtime and then essentially verifies the proof inside the runtime and then submits the result back to the contract. So without further ado, I'll just quickly switch to the VS Code, and I hope this is clear enough. Is it clear enough? People in the back, can you see it? Okay, cool. So if you look at our project, we have like lots of folders, but we're gonna start with the contract. So we have our Ink project. It's factors verifier. I'll call it factors verifier. And essentially, this is how the Ink smart contract looks like. So we have our constructor, and as part of constructor, we submit the image ID. It's essentially an identity. It's identity hash of the verify function that allows you to verify the proof. And then we store it in a contract storage. And then we have another simple function, verify via extension, which essentially takes a slice of U32 bytes and then submits them to the chain extension. Then essentially we are calling the chain extension function and returning the result. And then if the result is okay, then we have a flag called verified. And then if the proof has been successfully verified, we basically update the storage value and return back to the caller. And then I wrote also a very simple function that allows you to retrieve the result and essentially return the value of the verified flag. Then we have our prover project, which is RISC-0 project. Again, I don't really have enough time to explain exactly how RISC-0 works, but the short summary is RISC-0 is a project that allows you to take an arbitrary computation and essentially compute a Stark proof that can be verified in any sort of environment. And the whole idea is also, the reason it's why I call RISC-0 is because before producing a Stark proof, it essentially emulates the program on a RISC-V architecture. So it takes the program, compiles the RISC-V target, and then instrument the code and produce the Stark constraints, which can later be verified. And then I'm just quickly gonna go through the project. So we have our prover code. In this case, we have a simple factors problem where we essentially want to prove that some sort of party knows the factors of the number without actually revealing those factors. And you can see the code, it's very simple, very trivial. Then we have another project that essentially takes this computation and produces a proof. Then I wrote a bunch of code that essentially submits this proof to the contract. And then Now let's look at the runtime. I'm just going to go through the most interesting part. Here we have a chain extension, and if you look at the Rust project, I added a RISC-0 ZKVM dependency. I had to tweak it slightly. I'll explain in the limitation sections what exactly I did. And in verify extension, what we're essentially doing, we are reading the bytes from the environment. We decode them into the actual data structure, and then essentially we are proving the result, and then we are verifying the receipt, and then returning the result back to the caller. And the other part is just the boilerplate code that just encodes and decodes values. So you can see here, we decode the slice into receipt, which is a special data structure, a part of ZKVM library. And then I just call the verify function. And if the proof is invalid, the dispatch error is returned back to the caller. So without further ado, I'm just going to show a little demo how we can do that. So first, let's run our node. Then what we want to do, we wanted to run our proof and then generate image ID, which we then later going to use for instantiation. How are we doing with time? Okay. Yeah. In the meantime, while we're taking time to compile, it's always the Rust program just waiting for the result of compilation. So what we're going to do, first we run the node, then we run the prover, we generate image ID. We use that image ID to instantiate the contract, and then later we use this contract address to run the proof again. It just automatically submits, encode the proof and submit it on chain. If the compilation, yeah, demos never work on stage. Yeah, let me just rerun it. Okay. Okay, so we've got our image ID, and for now, I'm just going to copy it from the console, and then I'm going to go to the contracts project. I'm not going to compile it because I already compiled it. So what I'm going to do, I'm going to instantiate it and replace and specify the image ID as the argument. Our dry run has been successful. We submit it. Take a couple of seconds to actually get into a block. Okay, so we've got our contract address. But before I do that, I'm just going to call another function, cargo contract call. To verify. Oh, my bad. So the result is false. So right now we haven't verified proof yet. So if the proof verification is successful, the result is going to be true. So okay, we've done that. Now we go back to our prover and we specify contract address. Just going to run the proof again, just submit the proof on chain. Yep, okay, so the transaction is in block, so now we can go back and call it again, and you can see the result is true. So we successfully verified the proof, submit result back, and that's the end of the demo. I know it's a little bit not as exciting as it could be, but here we go. So talking about limitations, I actually first tried to verify the proof directly inside the contract, not through the chain extensions, and there are certain limitations that come with it. So first, the static buffer in Ink right now is limited to 16 kilobytes, but as you know, the Stark proofs are insanely large, so the proof I right now submitted is of the size of 55 kilobytes, and this is just the simple factors problem. Then secondly, I had to also tweak RISC-0 library, because it doesn't actually support compilation without standard library completely. So I had to remove a bunch of lines and like errors and serialization to make it no-STD compatible. Then, as I mentioned before, Stark proofs are large. 55 kilobytes is a lot, and I'm not sure like how much weight it's going to take and like how much block space it's going to take. And you know, this is the kind of open question we can target. I'm sure I've heard that you can also run a recursive proof that can compress the size maybe like 2 times, 3 times, but it's still a lot. Then also we have lack of optimized cryptographic primitives in Ink. And what I mean by that is that in Solidity you have so-called precompiled contracts, which are more gas efficient, and it allows you to work with cryptographic functions in a more efficient way, in a more gas efficient way. And in Ink right now, the only way you can do that is to use the chain extension. But in order to use the chain extension, the substrate developers essentially need to expose those cryptographic primitive and functions. There are a couple of issues to support some of the signature verifications, but again, this is currently unstable, and there's work to be done in future. And point 5 is, to be fair, writing chain extension can be cumbersome. There's a lot of boilerplate code needs to be written. You need to encode values, you need to decode values, you need to write a bunch of like wrappers around and add chain extension to your runtime. But it also requires the commitment from the substrate developers. And if you are basically a smart contract developer on some chain, then you essentially have no control over chain extension. If the substrate developers do not expose certain functionality, then you're out of luck. And the road ahead, how we can basically address those issues is, right now there's open issue on making static buffer configurable. So as a smart contract developer, you can essentially customize the size of the buffer and increase it to your needs. Finally, I'm going to talk about specifically the prover. Proving smart contract can be a little bit slow. Specifically, you would not be able to run, to compile and run Stark proof inside the web browser. But Fowler has this interesting concept of off-chain workers, and potentially what can be done is that you can maybe essentially compile and generate a Stark proof inside the Fowler off-chain worker and submit it as an on-chain transaction. This can be possible, one of the ideas to explore. Then also we started introducing RISC-V support. We actually introduced it for the different reason to do with deterministic compilation, but it can be also an option that we can essentially potentially use RISC-0 in combination with RISC-V and actually turn Ink smart contracts into ZK smart contracts. But again, this is just my ideas, and I'm not sure how feasible they are, but again, some topics to discuss. And I'm just going to summarize the talk. I know I'm a little bit over time, but key takeaways: that Ink is awesome. It's Rust. If you haven't tried, give it a try. It's super simple. If you came from Solidity, you can, some of these concepts are very similar: storage, events, messages, they're all kind of similar. We have also documentation. I'm going to show it on the last slide. Second point is that with RISC-0, it's proven that writing ZK code can be actually easy, relatively, and then it will become easier over time. And there's certain open challenges that can be targeted, but that's what personally excites me. Then, as I said before, there's definitely room for improvement in terms of the proof size, in terms of the technology, and compatibility with different stacks and ecosystems. Number 4 is that with Fowler and then potential other off-chain parachains, we can essentially use Ink as an off-chain worker and then potentially generate a proof off-chain and then maybe verify it on-chain using the same Ink language. And number 5, I think the groundwork has been laid. There's already enough proof of concept in the field, and the question for us, the kind of task for us, is take on this work and potentially develop on it further, play around, and essentially see what's feasible. I know Aleph Zero has been doing a lot of work around zero-knowledge proofs. They're doing a little bit more custom stuff with circuits, but I think they're also now working on proof of concept for the chain extension that allows you to verify proofs inside the Ink smart contract. And thank you very much for sitting through my presentation. So I have the QR code on the left is for the demo. The QR code on the right is for my Telegram. I have GitHub, LinkedIn. Always happy to connect and chat further around the topic. Again, if you want to learn more about Ink, go to use.ink. And yeah, thank you very much. Any questions if you have time? No? Okay, sorry. Thank you very much.